about now. Also, fair warning, my son is absolutely crazy right now. You might hear him yelling and screaming his little head off. It happens. Okay, so let's get into the Carnot cycle. Okay, so the Carnot cycle is predominantly used by engineers. So this is kind of getting into that Kelvin statement of the second law. But all the same, this is, I think, still important for chemists to have some familiarity with the Carnot cycle because engineers, learn from us on how to do these various cycles, how to make better, more efficient machines. Okay, so this is named for Seti Carnot, a French engineer. And he postulated this, this cycle. So much like we talked about in this previous slide, right? This path integral cycle, where now we're going to start at point A. And if you follow the lines here, we make it down to point B, then C, then D. Then we go around this full cycle. Okay. And so what we have to make this cycle, I'll try to highlight this. Okay, we have, as you can see, adiabats in purple and isotherms in blue. We remember that adiabats fall off more steep than isotherms. Okay, and so, right, to take note of the cycle, we're going to go all the way around here from A to B, then from B to C, then from C to D, then from D to A. Okay, so let's talk about all of that stuff. So at point A, so to go from A to B. Okay, we recognize because that's going on an isotherm, that has to be isothermal expansion. Look, the volume is getting bigger. Okay, and particularly we note that that has to be reversible isothermal expansion because it's following this Boyle's law curve, right? It's not irreversible, where it's occurring at a constant pressure. It's following the Boyle's law curve, so that's reversible isothermal expansion. Okay, and I'm going to note that we can also see from these two isotherms right here, this upper isotherm has to be a hotter temperature that I'll say TH than this lower isotherm. That's got to be at TC. Remember your mathematic activity when you plotted the ideal gas law, those family of curves, and what happens with temperature. Okay, so this is occurring isothermal reversible expansion at TH. We'll just say that's a hot temperature, a temperature greater than TC. Okay, and we also recognize, right, to make this isothermal, if we know that work is less than 0 because it's expansion, then that means Q has to be greater than 0. Okay, so now I will draw on this line here. Let's switch colors. I will note that heat, I'll say QH, heat is going in. So that's a positive QH to make that expansion isothermal and reversible. Okay, so now let's see. So that takes us from A to B. So now how do we get from B to C? Okay, so to get from B to C, that's occurring along the adiabat, and it's following this kind of Boyle's law behavior. So that means it has to be reversible. So that's reversible adiabatic expansion, because if you note on the volume scale, the volume is still getting bigger. So that's reversible adiabatic expansion. Okay, and we will note here just a few things to note, that the total change in entropy is 0 because it's reversible, right? So that is also applying to situation number 1. But we also note that there's a temperature change. So the temperature has to go from T hot to T cold, right? As we noted on these different isotherms. Okay? So now what's happening when we go from point C to D? So to get from C to D, this is now going to be reversible isothermal compression. Because now we note we're going this way, so the volume is getting smaller. Like, let me highlight those arrows. Okay, so the volume is getting smaller. And so we also note that this is happening at TC. It's happening at the colder temperature. And I also want to note that because it's compression, work is greater than 0. And because it's isothermal, the heat now has to be less than 0. So that means now in this cycle, heat is leaving the system. I'll indicate that by drawing an arrow that looks like this. So we now know that heat has to be leaving this system in order for the compression to happen isothermally. So I'll say now negative QC. Okay? And then now finally, to go from D to A, this is still occurring at constant total entropy. All right? Just as a reminder. And we can see that it's being compressed along an adiabat. So that means it has to be reversible adiabatic compression. And also the noting that delta S total equals 0 along that process is because no heat is leaving the system. So I said that wrong. So that's why I'm just putting S total on number 2 and number 4, because heat is either entering the surroundings or leaving, heat is entering the system and this number 1, and heat is leaving the system at this number 3. So S total actually can't be 0 because now there's something going on in the surroundings. All right? And we also note here that temperature has to increase. It has to go from TC to TH. Okay? So what does all of this mean? What do we get out of this cycle? What do we learn? Okay? Well, as it turns out, what we learn, what I want to prove to you, QH divided by QC, if I look at the ratio of the heat that goes in to the heat that goes out, it can be shown for an ideal gas that this equals negative TH divided by TC. Okay? So that's actually a pretty powerful result. That actually has significance. And the significance there is related to the bigger picture of this Carnot cycle, which I will get to momentarily. But the way that we prove this, okay, we note that QH is going to be the opposite of work, okay, for isothermal reversible expansion. The work for isothermal reversible expansion is the nRT, natural log V. Okay, so that means the Q is just a positive version of that, which is nRT H and natural log of the final over the initial VB over VA. Okay, and then similarly we can say QC. Let's see here. We can say QC is the negative version of that. Okay, natural log of VD over VC. All right. And what we also know, I'm not going to show this completely. I just want to show you where it connects from. We also know in the adiabats that the volume at A, and so remember this is TH, TC, the volume at A times the hotter temperature raised to some constant equals the volume of B times the temperature, the colder temperature, raised to some constant. Okay, so let's see, did I get that right? Let's see here. VATHC. Oh, excuse me. I need to be looking at the adiabats, not the isotherms. Okay, so that's why I did that wrong. So it's got to be now the volume of D. I've got to do this along the adiabat. The volume of D, TC, raised to this constant. And then in the other adiabat relationship, the volume at B times the temperature, the hot temperature, raised to some constant, is equal to the volume at C times the colder temperature, raised to some coefficient. Okay? And then I'm not going to finish this off. The rest of it is just algebra, but it's now substituting these volume ratios and canceling. And what you end up getting is this relationship. So in other words, in this Carnot cycle, in this full cycle, the heat in and the heat out can be directly related to the change in temperature. That's the big picture that I want you to connect, okay? And where this is important to the Carnot cycle is the following, okay? Is this picture right here. And in thermodynamic efficiency. So the second law implies that all reversible engines have the same efficiency regardless of their construction. That's true. And it's related to that heat in, heat out, temperature hot, temperature cold. Okay? And I'll show you, I'll just give you the definition of thermodynamic efficiency. It gets the Greek letter eta, which is the work performed divided by heat absorbed. Okay? So that's equal to the absolute value of W divided by the absolute value of QH. So let's think about this now. So suppose we have this engine. Okay? So we have some hot source. So this could be from the combustion of a fuel, right? For example. And so this hot source delivers some amount of energy. Let's say it delivers 20 joules. 20 joules of heat is transferred. Well, we know because this heat is being transferred spontaneously, not all 20 of those joules can be converted into work. It is impossible. It's a violation of the Kelvin statement of the second law. And in fact, the Kelvin statement of the second law comes from this. It comes from this Carnot cycle consideration. Okay? So we know some of that heat has to be dispersed, and we can disperse it out into some cold sink, some reservoir that can absorb all of that heat. And so suppose 15 joules of that 20 is lost to the cold sink, and only 5 joules is absorbed as work. Okay? So what is our efficiency from this situation? All right, well, the work performed was, I said 5 joules. I think in the book it says kilojoules. It doesn't really matter. Let's just suppose it's joules, okay? So our efficiency is going to be 5 joules, right, over the heat that we supplied from the hot source, which was 20 joules. And these are all in absolute values. We know that technically the heat will be positive and the work will be negative, but it's all about the absolute value, okay? So that means this machine was 25% efficient, which sounds pretty terrible, but that's actually typical. The internal combustion engine, so the engine in your automobile, they're about 20 to 25% efficient. That's very typical, okay? And so why does this matter? How do we get to all of this? Well, as it turns out, let me see what slide's next. Yes, so as it turns out, I'm not going to derive this, but the bigger picture of what's going on here between this and the work that Lord Kelvin did, they were able to actually work out the thermodynamic temperature scale based on this idea that regardless of the construction of the machine, all machines have the same efficiency, the work performed divided by the heat delivered. Okay? And so this allowed Kelvin to come up with a thermodynamic temperature scale, which goes as follows. T equals 1 minus eta times temperature of the hot source. So this is a very generic equation. Okay? And so what Kelvin ended up doing was saying, well, if I set this to the triple point of water, and he said the triple point of water because there's going to be no latent heat associated with any phase transitions. So he said set this to 273.16 Kelvin. I know you want to say 273.15, but he set it to 273.16 Kelvin. And regardless of the machine, it does not matter what the construction is. This will give you a universal temperature scale because now the temperature of this cold object, we know, so that's where we're going to get this. So TC will end up equaling this situation, right? And what it allowed them to do was put together a range of tests. You know, they didn't know this number, 273.16, but he was eventually able to come up with that number, 273.16, as the absolute temperature scale. Really, we know that it was based on this, right? 0 degrees Celsius equals 273.15. And I don't think that I'm explaining this very well, but the whole point is this whole scale was actually based on the Carnot cycle and the efficiency of work that you can do. Okay, so temperature is actually a secondary effect. Heat and work are the primary thing that's going on there. All right. And so the last thing that I want to describe, and so again, you know, just to hammer this home, right? If they knew, for example, the way that they worked this out is if they knew how much heat was being delivered and they knew how much work was being performed. Okay, so those are the two things that they can measure, heat being delivered and work being performed, and they get this efficiency as a result, they calculate the efficiency, then they can predict what the temperature of the cold sink will be. And using this idea, the 0 equals 273.15, and measuring a whole range of efficiencies, so heat and work performed, that's how that Kelvin temperature scale was able to be put together, which is pretty cool.